a way for early mammals to avoid either competing with them for food or becoming less themselves. This has become known as the nocturnal bottleneck hypothesis. In evolution, a bottleneck occurs when a population's genetic diversity becomes reduced, in this case, as a result of adapting to life in the dark. In studying the genomes of modern mammals, scientists have determined that not only do we have reduced vision, we also tend to be missing certain genes that protect our skin and eyes from damaging UV radiation. Color vision and UV protection are both really helpful if you spend a lot of time in the sun, but less important if you're active at night. In this case, all or most mammals are thought to have lost these daytime traits during the Mesozoic. So scientists suspect our mammalian ancestors may have spent most of the Mesozoic in the dark. Then, when the dinosaurs' reign ended and mammals finally got their time in the sun, they were working with limited genetic tools for adapting to daylight. Some of the genes that enabled daytime activities had been selected out and were long gone. So even though many mammals are active in the daytime now, their DNA is still sort of stuck in nighttime mode. Only certain mammals, like primates, have separately evolved more complex color vision, and with it, more colors on their bodies. Our mammal eyes may never be able to see colors as vivid and varied as birds' eyes can see, but that's a trade-off that allowed our ancestors to survive living alongside their ancestors. Fortunately, we humans can always add a splash of color with a favorite sweater.
We operate as a team of teams. Full-time, part-time, in or out of uniform. Because greatness can come from anywhere. But when you have the right teams in place, it comes from everywhere. Join us.
Well, I guess surviving is a pretty good reason to come in boring colors, especially when you realize that some animals come in bright colors for some kind of horrible reasons. Roly-polies or pill bugs. They're usually dark gray, but sometimes they come in a lovely vivid blue, which sounds really nice and beautiful until you learn what causes that. Here's Michael with the details. You might call them wood lice, pill bugs, potato bugs, or roly-polies, but they aren't lice or bugs. They're not even insects. They're terrestrial isopods, the only fully land-dwelling crustaceans. And they come in all sorts of colors. There's brown, light brown, black. Every once in a while, though, you might get lucky and find a brilliant blue roly-poly crawling around in the dirt. But your good luck is their bad luck, because that blue comes from a virus. And when it makes them colorful like that, the virus is almost always lethal. The viruses that turn roly-polies into roly-blueies are part of a larger family known as iridoviruses. Iridoviruses can infect all sorts of vector forms, animals whose body heat primarily comes from their environment, including crustaceans like our friends the pillbugs, true insects, reptiles, and fish. And at least among the invertebrates on that list, the most obvious symptom is a noticeable color change both inside and outside the animal. Infected animals can turn blue, green, yellow, red, or just be kind of shimmery depending on the virus. Now, on its own, that isn't too remarkable. Plenty of illnesses and infections change an organism's color, but most infection-related color changes come from some sort of pigment, a chemical that reflects certain colors and not others. Iridoviruses don't use pigments. You can't put iridovirus.
That hurt. Yoda.
viruses in a test tube and extract a blue substance. That's because the blue of infected pill bugs is an example of structural color. It's the arrangement of the viruses inside an animal's cell that determines what colors the cell appears to be. And ultimately, it all comes down to the wave-like properties of light. Waves can interfere with each other, reinforcing or canceling out depending on the way that the crests and troughs line up with one another. And that interference can alter what color is perceived. For example, red light's wavelength is about 700 nanometers. So if you had two semi-reflective layers of something, like layers of glass, separated by about 700 nanometers, the crests of the red light reflected by one would overlap with the crests of red light reflected by the other, making it seem like the thing is tinted red. But if the layers were separated by about 350 nanometers instead, the crests reflected by one would overlap with the troughs reflected by the other. No red light would come out at all, even though both layers are reflecting red. And the same goes for if you have individual atoms doing the reflecting instead of layers of glass. So that's structural color. The color you see doesn't just depend on the colors that are reflected, it depends on the physical arrangement, separation, and reflective properties of whatever's doing the reflecting. You can find structural color in butterfly wings, birds, beetles, and plenty of other species. And you can find it in animals heated by iridoviruses. That's because the viruses don't just spread all over the place when they reproduce inside a host animal's cells. They arrange into rows and larger structures, a lot like atoms do in a crystal. Smaller viruses tend to pack closer together, leading to a blue tint that's seen in animals like roly-polies. Larger viruses tend to spread out more, giving us redder animals instead. Iridoviruses have one more curveball to throw, though. Sometimes they cause this kind of characteristic color change, but usually they don't. Two animals of the same species can even get infected by the same kind of iridovirus, and one might change color while the other doesn't. These are called covert infections, and scientists still aren't sure what makes the viruses go down one path or the other, partly because they're not sure why iridoviruses color animals in the first place. Iridescent infections are easy for other potential hosts to avoid, which could potentially make it harder for the virus to spread. However, a bright bug is more likely to get eaten than one that's well camouflaged, and a predator that eats an infected bug in one place could carry the infection elsewhere. So some scientists think that obvious colors help the viruses spread far and wide, while covert infections let viruses move around within a single population. It's also possible that the colorfulness of the viruses isn't an adaptation in itself. Patent infections, the ones that cause color changes, happen when the virus reproduces really quickly inside a host's cells, while covert infections tend to be when the virus reproduces more slowly. And it could just be that when lots of viruses cram into a cell, it takes less energy to arrange like a crystal than it would to do something else. What we do know is that patent and covert infections tend to have different symptoms. Patent infections are just about universally lethal, but they don't usually go full-on pandemic and kill whole animal communities. They just consistently infect small percentages of certain species, anywhere from 1 in 100 individuals to 1 in a million. Covert infections are much more common. Estimates range from 10 to thousands of times as common, depending on the host species. And they're not nearly as lethal as patent infections. They usually impact things like an animal's ability to move around or reproduce. Whether patent or covert, though, iridoviruses can have some pretty big ecological effects. They've killed off whole populations of tiger salamanders and bass, and they've been found in bee colonies that have suddenly died, suggesting they might play a role in colony collapse disorder, too. Understanding the epidemiology of these viruses could help researchers predict and prevent outbreaks in species we don't want to lose, like bees. And it might even allow scientists to get the viruses to do some good, like control invasive pests. In the meantime, they give physicists and biologists something to talk about at a dinner party. Well, in the end, at least those viruses might be useful. It doesn't make life easier as a roly-poly, but it's a silver lining at least. Thankfully, not every blue in nature means death is knocking on your doorstep. Like with reindeer. Reindeer eyes, specifically, unless you know about some species I don't. Here's another one from Olivia.
Shine a light into the woods at night, and you might see the glow of eyes staring back at you. But the eyes aren't actually glowing. They're reflecting light off a special layer of tissue found in some animals called a tapetum lucidum. The color and shape of this eye shine can tell you what's peering at you from the darkness. But things are more complicated if you're in the Arctic regions of Norway, because there, reindeer change the color of that part of their eyes seasonally. That's right. The animals most famous for pulling Santa's sleigh have eyes that change color to help them see in the darkness of winter. Animals that need to see well in low light, like cats, raccoons, and even reindeer, all have tapetum lucidum. They sit in the back of the eyes, right in between the outer layers of the eye and the retina, the part that actually sees. These thin tissues act as reflectors, giving retina a second chance at absorbing light. Most animals have a particular particular color of eye shine, which depends on the composition and structure of their tapetum lucida. But the Eurasian mountain reindeer is different. It's the only one we know of that switches colors, changing from a summery golden yellow to a deep blue in winter. And scientists think that's a side effect of how their eyes have adapted to long periods of darkness. The Arctic summers where they live have 24-hour days, and the winters include long stretches of night. The animals compensate for this in part by making their retinas more responsive to low light in winter, and it's believed they can see some wavelengths of UV light. But that's not the most obvious adaptation. To see better when it's so dang dark, a reindeer's pupils open wide to let more light in, kind of like yours if you go into a dark room. But when a pupil stretches wider, it also flattens the front of the eye ever so slightly, which increases the pressure inside the eye. Since their pupils are constantly wide open during winter, that pressure builds up, squeezing the tiny collagen fibers of the deer's tapetum lucidum closer together, and this compression causes the color change. The tightly packed fibers strongly reflect shorter blue wavelengths of light, while the more spaced out ones reflect longer yellow ones instead, a phenomenon known as Bragg's law. Researchers can actually compress a dissected piece of the reindeer's eye with a tiny weight and induce the same yellow to blue color change. But the color isn't what's really important. Bragg's law. Researchers can actually compress a dissected piece of the reindeer's eye with a tiny weight and induce the same yellow to blue color change. But the color isn't what's really important to the animal. The compressed fibers also scatter light sideways through the retina instead of reflecting it out of the eye, increasing the amount of light the retina can absorb. While summer eyes reflect more than 95% of the light shown into them, winter eyes reflect only 40%. And that likely means the reindeer can see in what seems like total blackness. The only downside to this amazing feat is that because light rays inside the eye are more scattered, everything also looks a little fuzzier. But that seems a small price to pay. I wish I could trade a little blurriness for night vision.
T-Mobile is the leader in 5G. We also believe in putting people first by treating them right, so we up the benefits without upping the price. With Magenta Max, get our best plan for 5G. With unlimited premium data that can't slow down based on how much smartphone data you use. And taxes and fees are included. You won't get that from anyone else. Right now, pay zero cost to switch. And for your phone, we'll pay it off. Only at T-Mobile, the leader in 5G.
Adventure time.
Wow. How you doing? How are you?
Aw, I feel like reindeer need cute little reindeer glasses. Speaking of very cute things, Siamese cats. They have those adorable dark mittens and the little brown ears and a cute little face. But what gives them their distinctive look? Here's one more episode with a surprising, and my father-in-law let me know, absolutely mind-blowing answer. Seriously, you love this episode. From a tiger's stripes to a jaguar's rosettes to a tabby's whorls, cats come in lots of different colors and patterns. Normally, we imagine that the way an animal looks is inherited from its parents, basic genetic stuff, but sometimes the origin isn't so simple. Like the coloring of some domestic cats is tied to their sex. That's why orange cats are much more likely to be males, and calicos and torties are almost always female. But Siamese cats are especially interesting because their recognizable coloration is actually dependent on temperature. Animals get their dark color because their bodies produce melanin. Melanin is the same protein responsible for variation in human skin tone and making you tan, and it's produced thanks in part to the enzyme tyrosinase. Normally, this enzyme does its job pretty well, but in some breeds of mouse, rabbit, and cat, and even in some human cases, the enzyme doesn't quite work the same. In particular, virtually all Siamese cats have a mutated version of the gene that codes for this enzyme. So their tyrosinase is extremely sensitive to temperature. So sensitive, in fact, that it unfolds and no longer functions functions at the average cat body temperature at around 38 degrees Celsius. That isn't great for the enzyme. Can't really do its job anymore, but it does give the cats their adorable coloration. Without functional tyrosinase, no melanin gets produced, so most of the animal's fur is a creamy white. It's essentially albino. But Siamese cats also have those super cute boots and that little brown mask, and that's because tyrosinase is functional in their extremities, like their tails, legs, noses, and ears. Compared to their volume, these parts of the body have a larger surface area for heat to escape from. So these small and slender body parts lose heat more quickly than the cat's central core. This is just like how your fingers and feet and nose are the first things to get cold when you step outside, or how a narrow icicle is going to melt before a compact ice cube made of the same volume of water. In a cat, this means that the face, limbs, and tail are just a few degrees cooler compared to the rest of the animal's body. And that difference is enough to preserve delicate tyrosinase's shape and function, allowing it to color the fur. If you ever get to see a newborn Siamese kitten, you can actually watch this process happen live. When the cats are born, they're totally white, since the inside of the womb is a uniform and toasty 38 degrees Celsius or so. Out in the world, though, the temperature around the kitten is cooler than its body, so it loses heat to the environment, especially from its tiny toes and tail. Within a few weeks, the characteristic Siamese color pattern starts to emerge as new fur grows and tyrosinase gets to work in the cat's extremities. So unless you're keeping mittens on your kittens, Siamese cats will develop their trademark coloration. So unless you're keeping mittens on your kittens, Siamese cats will develop their trademark coloration, all thanks to this delightful mutation. Cats are, unsurprisingly, just so great. Thank you for watching this episode of SciShow. Compilations like this make me realize how much content we have put out over the years, and we couldn't have done it without the support of our patrons on Patreon and our channel members. If you support SciShow, you're helping put more free educational videos out into the world to be watched by people who love them, to be used in classrooms all over the place, and we are really grateful for that. If you want to learn more about supporting the show, you can go to patreon.com/SciShow.
And with that,
early game we got from Outset, and you're going to notice that this cutscene is a bit weird. There's just text.
It's time to get ready. From showing up for your loved one's biggest moments, to finally getting to say I do. From getting back to the office without the sweats, to getting the gang back together on a Saturday night. For every moment that matters, Men's Warehouse is here to help you get ready.
Hey everybody, I'm Teresa.
And I'm Sarah
From LG CTS Motorsports.
And we want to hook you up with this Jeep that we customized just for you.
That's right, to support a great cause, we're back with Omaze to get...
This right here is the brand new glitch that was just found in Breath of the Wild. But answering this question of what this new glitch is and the impact it will have on the speedrun actually raises more questions than it answers. So that's what I'm going to be focusing on in today's video. We'll be taking a look at how this one glitch will change the speedrun as we know it, and also explain how to perform this glitch for yourself, since thankfully it is quite the easy glitch to perform. I hope you enjoyed the video. Oh, and don't forget to subscribe to the YouTube channel. To fully understand the impact that this glitch will have on the speedrun, we first need to take a look at what the current speedrun strats are like. If you dive all the way back to the launch of Breath of the Wild, you will notice that the time to beat the game was about an hour or so. And when taking a closer look into why the speedrun took so long, it simply comes down to how big the world is, and how much time the player spends running to get to each area of the game. So right from the start, the speedrun community put a lot of time trying to shorten these sequences. The first successful attempt to shorten the running speed came in form of stasis launches. By either getting hit by a fast-moving object, or grabbing onto a fast-moving object, you could cover...
Hello? What's up with you? Dang. Y'all still friends? That's that good friendship right there. I don't know, all my friends, I ain't got friends no more. All my friends. No, I don't. Because you make fun of me. And friends don't do that to friends. No, you be acting weird sometimes, I'm not gonna lie. No, you be acting weird. You going to your sister's birthday party? Of course I can. I was. It's grown ups there. Why you mad? Cause I ain't go to your baby party. You salty. Why don't you just leave the past in the past? Why don't you leave the past in the past? You ain't even answer my question. Just leave the past in the past. Okay. Are you bet? Alright. So when I show up, don't be like, oh, you ain't gonna. Hey, leave it in the past. Okay. A lot of people forgot who I was. Yeah. No food gonna be there. It's weird. Man, just put it on the three-way.
This thing is fun.
4193
Wow.
4096 87 is not available.
Drop 'em.
Four one nine three 409687 is not available.
Wow. The dishes. Man, I called you 3 times, and you ended my call 3 times.
I'm at work.
Dang, that's crazy.
What's up?
You was on the phone with Ebony, right?
Hello?
Hello? Can you hear me? Oh, I'm done trying to call that woman. She gonna have to call me. She keep hanging up. I'm done calling people. Y'all gonna have to call me. You heard?
Have you ever kept goldfish as pets?
Cover huge areas of the game and very
The fuse is lit! A festive reprise! Can't catch me! Time for a light show!
From whence you came? This is a new one.
Fire hazard! Here come the fireworks! Fuse is lit! Fire hazard!
Ever seen one of these?
Way I go!
The hunt is on.
Time for a light show!
blade. Attack! Got something for it.
The fuse is lit! Gotta watch it. Time for a light show.
Restaurant? That place isn't even worth mentioning.
Ad Astra Abyssal. Ad Astra. This realm is... If you ever have... This realm... If you ever...